Well, thank you very much for that kind introduction, and it's my privilege and honor to be a co-recipient of this year's King Faisal Prize. The history of humanity is closely intertwined with the history of pandemics, from the plague of Athens in ancient Greece, to the plague of Antonine and Justinian in ancient Rome, to the Black Death of the Middle Ages, the plague of the Incas in the 1500s, the Great Plague of London in the 1600s, the yellow fever pandemic in the 1700s, the cholera pandemic of the 1800s, the influenza pandemic of 1918 to 1920, and over the last 100 years, pandemics of Ebola, HIV, avian flu, SARS, chikungunya, Zika, COVID-19, Mpox, and surely there will be more moving forward. The most important countermeasures for pandemics are public health strategies as well as vaccines. And as stated eloquently by Stanley Plotkin, the impact of vaccination on the health of the world's peoples is hard to exaggerate. With the exception of safe water, no other modality has had such a major effect on mortality reduction and population growth. Classical vaccine strategies include live attenuated organisms, whole-killed organisms, and protein-based vaccines such as toxoids, conjugates, and subunit proteins. Over the last several years, there's been a revolution in vaccinology, the generation of gene-based vaccines, including nucleic acid vaccines such as DNA and mRNA, as well as viral vector vaccines such as adenoviruses and poxviruses. And these have really come to fruition and have shown their worth over the last several years during the pandemic. In December 2019, a new disease emerged from Wuhan, China, a pneumonia of an unknown cause. Within days, the pathogen was identified, and on January 10th, the SARS-CoV-2 sequence was released. On this day, there were 41 cases and 1 death reported, and these numbers were alarming enough to trigger vaccine development in many groups around the world. By mid-2022, instead of 41 cases, there were billions of cases, and instead of 1 death, there were over 15 million deaths worldwide, including over 1 million deaths in the United States alone. But the scientific community responded in a way that science has never responded before, in terms of a global effort to understand the virology and the immunology of this disease, the development of science-based public health measures, the development of therapeutics, as well as the development of vaccines. In the United States alone, there were 6 vaccines that reached clinical efficacy trials. The first 2 were the mRNA vaccines from Pfizer and Moderna. The second 2 were the adenovirus vector-based vaccines, the program that we were most closely involved in, the Ad26 program with J&J, and the program we just heard about from my co-laureate, Dr. Gilbert, ChAdOx1 with Oxford AstraZeneca, as well as the protein-based vaccines from Novavax and Sanofi. We initially generated the Ad26 vector platform not for COVID-19, but actually 15 years earlier for our long-standing efforts to create an HIV vaccine. And the development of an HIV vaccine started globally 40 years ago and is continuing until today. Unfortunately, we don't have an HIV vaccine yet. It provides major unsolved challenges for vaccinology. But HIV research has led to multiple of the technology developments that ultimately led to COVID-19 vaccines and others. We used Ad26 first for a pandemic response as part of the Zika virus pandemic. And together with our industry partner J&J, we developed an Ad26-based Zika virus vaccine. And we showed in a clinical trial in Boston that the Ad26 Zika vaccine raised neutralizing antibody responses in essentially 100% of individuals after a single immunization that lasted for more than 1 year, shown in the blue and the yellow. A second booster shot, shown in the orange and the dark blue, led to a substantial increase in these responses. So if we dial back to where we were thinking in January of 2020, we thought there was a strong rationale to develop a Ad26-based COVID-19 vaccine because the replication incompetent Ad26 vector platform had already been developed for multiple prior pathogens. The Ad26 HIV program was the initial development of the vector platform technology. The Ad26 Zika program showed the potential of a single-shot vaccine as well as the improved responses with 2 shots of the vaccine. The Ad26 Ebola program from J&J became a licensed vaccine and showed that mass production and global distribution was feasible without the need for a sub-zero frozen cold chain, which we reasoned was going to be very important for distribution of a vaccine worldwide. And the Ad26 RSV vaccine had just shown high efficacy in humans against a respiratory virus, suggesting that this might actually work for the newly spreading coronavirus. Our first study was actually a study to look at natural immunity, even before the vaccine studies began. And in a study in macaques, we demonstrated that SARS-CoV-2 infection in macaques could protect robustly against re-challenge. In a study, we challenged macaques with SARS-CoV-2. We measured viral loads in the lung, shown on the left. And then after recovery, we re-challenged them with a second exposure to SARS-CoV-2, and we showed substantial protection. Demonstrating natural immunity at a time when natural immunity to coronaviruses was quite debatable, we thought was very important because it increased the chance that all of the vaccine programs throughout the world would be successful, because it's much easier to develop a vaccine for a virus for which there is natural immunity. Then with the experimental studies with the SARS-CoV-2 vaccine, which became known as Ad26-CoV-2S, then we showed first in macaques that there was substantial protection against experimental challenge with SARS-CoV-2. And in a series of clinical trials that ultimately led up to the licensure study called Ensemble, which was a 45,000-person global phase 3 trial in 3 major areas of the world, North America, South America, and Southern Africa, there was 85% efficacy against severe disease shown here, which ultimately led to licensure of this vaccine and WHO qualification. In the United States, there were 3 major vaccines that were rolled out, at least early in the pandemic. The 2 outstanding vaccines, mRNA vaccines from Pfizer and Moderna, as well as the J&J vaccine. The data prior to Omicron showed outstanding efficacy against symptomatic infection for all 3 of these vaccines, 94 to 95% efficacy for all of the 2-shot versions of the vaccine, with the J&J vaccine also being able to be given as a single-shot vaccine with slightly lower 72% efficacy. The impact of the COVID-19 vaccines is truly indisputable. It's been estimated that over 20 million lives were saved by the COVID-19 vaccines in the year 2021 alone, really led by the Oxford AstraZeneca and the Pfizer BioNTech vaccines, but also millions of lives saved by the Sinovac, Moderna, Sinopharm, Sputnik, J&J, Bharat Biotech, and CanSino vaccines. And I will add that more lives have been saved by the adenovirus vaccines than the mRNA vaccines. But no discussion about the triumph of the COVID-19 vaccines can be complete without also talking about the challenges faced by the COVID-19 vaccines, including global health equity in the rollout, rapidly waning immunity, particularly with the mRNA vaccines, the emergence of viral variants, and the politicization and vaccine hesitancy that's emerged. I'll talk briefly about these first 3 topics and happy to answer questions about the 4th one. During the rollout of the COVID-19 vaccines, there has been greater global health disparities than in almost any recorded history of global medicine. By the end of 2021 and early 2022, over 70% of individuals in the United States and in most other wealthy countries in the world had received COVID-19 vaccines. And in fact, we had enough vaccines for 100% of the population and multiple boosters thereafter. In contrast, by the end of 2021 and early 2022, less than 15% of people in Africa received any vaccine at all. And so it's been said that we in the United States exported vaccine hesitancy more effectively than we exported vaccines. The mRNA vaccines, which have had a stunning impact in the Western world, actually had very little impact in the developing world in 2021. Very limited use of the mRNA vaccines in this time period, in a large part because of the frozen cold chain requirement, as well as other factors. And in the developing world, as was mentioned by Dr. Gilbert, the COVID-19 vaccines really were led by the ad-vector-based vaccines, particularly the AstraZeneca-Oxford vaccine, as well as to some extent the J&J vaccine. One of the most humbling moments we had in the lab was the first COVID-19 vaccine rollouts in South Africa, which actually were the first rollouts of any COVID vaccine in the continent of Africa, which was the Ad26 J&J vaccine on February 17th of 2021. And here, of course, announced by Twitter, like many things in the pandemic, Dr. Nigel Garrett reports on Twitter, immensely proud to deliver the first COVID-19 vaccines to healthcare workers in KwaZulu-Natal, Prince Mashani Memorial Hospital. Let's accelerate this effort and save lives. Here you see a picture of Nigel Garrett, Slim and Quraisha Abdul Karim, personally overseeing the first shipment of vaccines to South Africa at a time when there was an incredibly high mortality rate amongst healthcare workers in South Africa. And no other vaccines were available at that point in time. In the first day of the rollout, you can see a healthcare worker on the upper left, as well as the president of South Africa on the bottom right, receiving the vaccines. And there's a report, thank you for my vaccine yesterday, I feel great. We are so grateful and excited. And Nigel Garrett reports back, glad you're feeling fine, spread the word. The real-world outcome of this rollout, this demonstration project called Sasanki, was outstanding, 86% protection against death, including with a single shot of the vaccine. And so I think it's not an understatement to say that this vaccine saved hundreds, if not thousands, of lives of South African healthcare workers and essentially stabilized the South African healthcare system. Meanwhile, in our lab in Boston, we were studying the immune responses for all the vaccines that were being rolled out in the United States. The Pfizer vaccine shown in blue, the Moderna vaccine shown in green, and the J&J vaccine shown in black. And we observed that there were differences of kinetics of the antibody and T-cell responses elicited by these different vaccine modalities. In terms of antibody responses shown on the left, the mRNA vaccines generated incredibly high early antibody responses, shown in the blue and the green. But what was not known at the initial time of the rollout of these vaccines is that for reasons that are still largely unknown today, the mRNA vaccines have a very short durability of these responses. And these antibody responses decline quickly and sharply over time. You can see that by 6 months and even by 8 months, there's about a 2-log drop in these antibody titers. The Ad26 vaccine had a very different profile. I'll see if I can have a pointer here. Oh, here. So the J&J vaccine with Ad26 had a very different profile. Initially, the antibody responses were much lower, about 2 logs lower than the mRNA vaccines. But these really persisted over time better. So by 8 months, then these responses were really quite similar, if not even higher. The T-cell responses, which largely were underappreciated in terms of their importance, here the CD8 T-cell responses, were more durable than the serum antibody titers, with the Ad26 vaccine giving higher CD8 T-cell responses than the mRNA vaccines. So the durability of the Ad26-based vaccine became more apparent as time went on. And an effectiveness study in insurance claims in the United States demonstrated that the effectiveness of this vaccine really was maintained very well over time. Here, the efficacy, it did not start at 95%, started at 72, 73%. But actually this was maintained very well over this period of time through the Delta wave. And a follow-up study from the Department of Health in North Carolina showed the relative durability of the Pfizer and the Moderna vaccines shown in blue and red, and the J&J vaccine shown in green. Initially, early after vaccination, the highest efficacy was from the Moderna vaccine at about 90% and the Pfizer vaccine at about 75%. The J&J vaccine was slightly lower at 70%. But over time, you can see that there is a difference in the durability of these vaccines, with more rapid waning of immunity with the mRNA vaccines, down to essentially 0% for the Pfizer vaccine after 14 months in people who were not boosted. For the J&J vaccine, it basically crosses the Pfizer line at about 4 months, crosses the Moderna line at about 8 months, and was clearly superior by 12 months and beyond. The totality of efficacy data in the United States compiled by the CDC is really similar to this, in that here the CDC reports over time the incidence rate per 100,000 population. The unvaccinated individuals are shown in black through the Delta wave and the Omicron wave, and the vaccinated individuals are shown in red for the J&J vaccine, blue for the Pfizer, and green for the Moderna vaccines. Basically, all three of these vaccines did their job and substantially reduced the incidence of symptomatic COVID for the entirety of the pandemic. If you look at the fine differences, you can see that early on during the Delta wave, the breakthrough rates of the J&J vaccine were slightly higher than the other vaccines, as evidenced by the red line being slightly higher than the blue and the green line. But over time, what happens is that these curves crossed, and over the last year, during the Omicron wave, this was really inverted, with the lowest breakthrough rates in individuals who received the J&J vaccine, and the highest breakthrough rates people who received the Pfizer vaccine. The history of the SARS-CoV-2 pandemic is really the history of variants now. And early on in the pandemic, the ancestral sequence from Wuhan was rapidly replaced by a variant called D614G, which is shown in yellow, which is a single point mutation that appears to have increased transmissibility. Then in spring of 2021, there was a period where there were multiple variants emerging in different parts of the world, and this eventually gave way to the Delta variant shown in purple, which dominated throughout the world in summer and fall of 2021. And then what happened, there was a rapid shift around December, January 2021, 2022 to the Omicron wave, which is shown in the red and the very different colors afterwards, as sort of a rapid sequence of subvariants. These were characterized by accumulation of mutations in the SARS-CoV-2 spike protein that led to progressive and profound escape from neutralizing antibodies. Here is our data showing the neutralization escapes from BA1 through BA5, and this is very similar to data reported now by dozens of laboratories throughout the world, showing that in both a vaccine cohort as well as an infection cohort, there were substantial reductions of neutralizing antibody titers by these different variants. BA1 and BA5 was even greater escape than BA1, about 10 to 20-fold lower neutralizing titers compared to the original ancestral strain. The original two-shot vaccines, and this is the Pfizer vaccine, really had no neutralizing titers for any of the Omicron variants, and really a third boost was really needed to generate any neutralizing titers at all. The substantial reduction of the neutralizing titers led many people to worry whether essentially the bulk of vaccine protection would be lost. And in fact, there was very little protection against any of these Omicron strains for any of the vaccines against acquisition of infection. But what was initially surprising and really quite reassuring is that there appeared to still be substantial vaccine protection against severe disease, even against Omicron. And this is some of the first data that really established this point from Glenda Gray and colleagues in South Africa, where the first Omicron surge occurred. And they demonstrated that two-shot version of the vaccines, the two vaccines that were rolled out in South Africa were the J&J vaccine and the Pfizer vaccine. And after two shots of these vaccines, there was still substantial protection against severe disease, despite the absence of essentially any detectable neutralizing antibody titers. Here you can see that against hospitalization and ICU care, the J&J vaccine still gave 72 to 82% protection. The Pfizer vaccine gave about 70% protection. And so how can these vaccines still give substantial protection against severe disease, even in the absence of high neutralizing antibody titers? It certainly suggests that immune mechanisms other than antibodies are important for protection against severe disease. And we believe that one of those immune mechanisms are T-cell responses. Here we showed in early January 2022 in data that was basically simultaneously published by 4 different groups worldwide, that although Omicron there was substantial neutralizing antibody escape, then the vaccine-induced T-cell responses remained highly cross-reactive. And so here we showed that for both the J&J vaccine on the left and the Pfizer vaccine on the right, that the T-cell responses to Omicron, shown in green, were virtually indistinguishable to the T-cell responses against the ancestral strain, shown in black. Thus, while Omicron significantly escaped neutralizing antibody titers, it really did not escape T-cell responses. And this is shown here with very good correlations of T-cell responses between the ancestral strain and the Omicron strain. To try to establish this further, we looked at some preclinical studies to try to establish whether we could essentially formally demonstrate a role of CD8 T cell responses in vaccine protection. And so this is a study we published last spring, in which he looked at the role of both neutralizing antibody titers and CD8 T cell responses for vaccine protection against Omicron challenge in monkeys. And we looked at different prime boost combinations with the Pfizer vaccine and the J&J vaccine. I don't have time to talk about all of the details. These data are published. But the protection basically suggested a role of both antibodies and CD8 T cell responses. And so here, this is a hypothetical two-dimensional immunologic space in which each of these dots represents one of the macaques in this challenge study. And the pre-challenge Omicron neutralizing antibody titer is shown in the x-axis, and the pre-challenge Omicron CD8 T cell responses are shown on the y-axis. And the black dots represent animals that controlled the vaccine challenge, and the red dots basically represent vaccine failures. And so the point of this slide is to show that the vaccine failures really clustered in this bottom left corner of the graph. And so we can place a dotted line to essentially create this hypothetical immunologic space that is essentially vaccine failures. And this essentially is animals that both simultaneously had low antibodies and low T cell responses. To show this even more directly, we did what's so-called a CD8 depletion study to look at mechanistic correlates of protection. And we vaccinated animals with a J&J vaccine or a sham vaccine, and then we either treated with a CD8 depleting antibody or a sham control antibody prior to a SARS-CoV-2 challenge. And what we showed was that CD8 depletion in vivo actually abrogated vaccine protection. So this was a high-dose delta challenge, and so we looked at viral loads following challenge as the outcome, as opposed to frank protection against acquisition of infection. And both at peak and at day 4, these are viral loads in bronchoalveolar lavage. In the sham controls, they had high levels of virus, as you would expect, and the vaccinated animals that were not CD8 depleted had about a 2 to 3 log reduction of viral loads, indicative of vaccine protection. And in animals that were depleted of CD8 positive T cells, then the protection was largely lost, with viral loads more approaching the control group, demonstrating fairly directly of the importance of CD8 T cells in vaccine protection. Some of these ideas were recently discussed in a review article that I contributed to the New England Journal of Medicine, and this is our proposed model for vaccine immunity against COVID-19, that both antibodies and CD8 T cells are important for vaccine protection, but the relative role is different depending on the type of protection you're looking at. To protect against acquisition of infection, or to protect against asymptomatic infection, and probably also mild infection, this is a predominantly antibody-mediated phenomenon. And particularly to actually, frankly, block acquisition of protection, it's probably exclusively antibody-mediated. But the current vaccines really do not provide this type of protection against Omicron. There is really very little protection against acquisition of infection with any of the vaccines currently. However, fortunately, all the vaccines still have very good efficacy of prevention of severe disease and death. And this, in my opinion, really should be the goal of COVID-19 vaccination. And to protect against severe disease and death, it is almost certainly a combination of antibody and T cells, and I would argue a very substantial role of T cells. Together with John Wary, we reported in a Viewpoint article in Science that T-cell immunity is important for COVID-19 vaccines, and we tried to illustrate this to show that neutralizing antibodies and T-cells both contribute to COVID-19 vaccine efficacy. So when vaccines induce high titers of neutralizing antibodies, SARS-CoV-2 infection of the upper respiratory tract can be blocked, as shown here in the upper illustration, where here in the upper airways, if there's sufficient neutralizing antibodies, then virus is essentially neutralized and no infection occurs. This is largely theoretical, and with the current Omicron variants really doesn't happen with current vaccines. When neutralizing antibody titers wane or the virus has variants that evade antibody recognition, robust T-cell responses can kick in to block progression of infection to the lower respiratory tract. Here shown in the middle diagram, protection against severe disease, which is really the current goal of COVID-19 vaccines. Some of the virus is neutralized, but the remainder of virus that gets through is essentially eliminated by memory T-cells. And then severe disease occurs when there's low titers of both antibodies and weak T-cells, and the virus essentially gets by both of these lines of defense to cause severe disease in the lungs. So where are we currently in the pandemic? This is data from just yesterday from the CDC. In the United States, the virus has continued to evolve beyond BA.5, and BQ.1.1 and now XBB.1.5 have largely replaced BA.5 as the dominant SARS-CoV-2 variants in the United States and to a large extent throughout the world. These variants have demonstrated a progressive, even further escape from neutralizing antibodies. Here's data that we recently published demonstrating that BQ.1.1 provides a 7-fold higher level of antibody escape, and XBB.1 is a 20-fold greater neutralizing antibody escape compared with BA.5, which essentially is about a 200-fold antibody escape compared with the ancestral virus. So even peak responses following boosting are quite low for neutralizing antibodies, and yet hospitals are not filling up. And that's because we believe that the T-cell responses, which we reported previously, still remain highly cross-reactive to BQ.1.1 and XBB.1.5. Interestingly, are not really boosted with the mRNA vaccines, and so this largely reflects natural immunity at this point. So briefly in conclusion, the gene-based vaccines, the mRNA technology, as well as the adenovirus vector technology for COVID-19 have truly revolutionized vaccinology and have saved over 20 million lives globally. Adenovirus vector-based vaccines play an important role as part of the global COVID-19 vaccine arsenal due to their low cost, the lack of a freezing requirement, the robust durability, and the particularly good induction of CD8 T cells, which provides cross-reactivity against emerging variants, and therefore make them very good vaccines for global use. Scientifically, we believe that CD8 T-cell responses demonstrate substantially greater durability and cross-reactivity against variants than neutralizing antibody responses. But the field remains focused like a laser beam on short-term neutralizing antibody responses after a vaccine or after a boost. And while that is important, we believe that it's really the durability of the antibody titers and the durability of the T-cell responses that are likely the most critical parameters for long-term protection, particularly against severe disease with viral variants. I'll stop there and thank my team. This was from our research retreat just 2 months ago, and this is one of our first meetings in person as a group without masks on, thanks to a large part of the vaccines that were available. Thank you all very much. Happy to take any questions if there's time. Yes.
Thank you, Dan. Beautiful work. Are you suggesting that actually with the long-term immunity associated with the T cells, we do not need to have more boosters? Or maybe we don't need to have it so frequently? And then secondly, have you studied the effect of T cell immunity on different high-risk groups? Would that explain why some people will not respond so well even after they have been vaccinated if they belong to those high-risk groups?
Yes, very good questions. So first, boosting has been a very difficult topic that merges politics and public views and science and medicine. And it's clear that with the first 2 immunizations, there is very little induction of antibody titers against the later variants, and it really requires a 3rd shot. I think that is very important because that essentially broadens the antibody response, which is important in addition to T-cell responses, to the Omicron class of viruses. So I think that is a very important boost. After that, it's become much more difficult, and the role of boosting, I think, is quite clear for the elderly, the immunosuppressed, and people with severe comorbidities, because the waning of protection, including waning of protection against severe disease, is particularly rapid in those groups. So for those groups, I think it's important to get frequent boosts. Boosting has been much more controversial for the younger or the healthier population. And the benefits appear to be less and shorter lasting. So for the bulk of the public, then the long-term cellular immune responses, which are T cell responses as well as B cell responses, actually still provide substantial protection. There is, of course, some level of added protection with boosting, but the relatively added benefits are much less in the general population than in the high-risk population. And so where is the balance? And that's more of a policy decision than a science decision. But I personally believe that trying to roll out boosters every 4 to 6 months for the general population is probably not a winning strategy, largely because the population is not accepting of that. So I think that at most a yearly booster is probably where we're at now. And I think even that is arguably, the benefits are much less for the young, healthy population than for the elderly. But it is true, as your second part of your question, that the T cell responses are also different and less robust in the elderly and the immunosuppressed and the individuals with comorbidities. And so that's largely why that group remains susceptible to severe disease. I'm sorry, could you repeat your question, please?
Did you see any increased activity of CD4 helper cells with regard to interferon production?
Yes, so the mRNA and the vector-based vaccines induce both CD4 and CD8 T cell responses. The CD4 T cell responses are quite aligned with the neutralizing antibody titers. The CD8 T cell responses are quite different than the antibody responses. The CD4 T cell responses are functional and are boosted somewhat by subsequent immunizations.
But you'd say that the CD8 is more significantly activated?
Well, it's hard to quantitate. I would say that the data supports CD8 T cells more strongly. That's partially a function of the experimental models, because in macaques we can deplete CD8 T cells experimentally more easily than CD4 T cells. Also, classically, CD8 T cells have more of a direct antiviral function. But that doesn't decrease the importance of CD4 T cells, which mainly serve to support the antibody titers. But there is data suggesting that CD4 T cells can have direct antiviral activity, but certainly classically not as much as CD8 T cells. So I think formally, no one has really been able to do a relative comparison of the importance of CD4 and CD8 T cells, but the data set is stronger for the role of CD8 T cells at the moment.
Thank you. Another question is, I understand that the adenovirus vector is silicon, so do you not get an immune response against the vector which would reduce the effectiveness?
You do get an immune response against the adenovirus vector, but it is not sufficiently high to preclude at least a second boost. And those anti-vector titers also wane over time. So if you wanted to give 3 or 4 shots in rapid succession, then you would see attenuation of the body's response to the adenovirus vector. You don't see suppression with a second shot, and if you have yearly shots, then it's probably also fine because those wane over time. But if you needed to give, say, 4 shots within a year, then you probably would want to switch serotypes for the 3rd and the 4th shot.
Thank you.
Are there any other questions? Thank you so much, Professor Barouch.
Thank you.
For your lecture. I would like to request the Professor Leadership on stage to present Professor Dan Hung